Let's start with a simple example of applying this general forcing solution. So in this case, we are given all of the modeling parameters, the equivalent mass, spring constant, and damping coefficient right away. So that's going to make the modeling part much easier. And we are given this force profile that is acting on this spring mass damper system. So we are looking for the steady state behavior only of the system. So we just want steady state. We're not going to need to, in this example, do the homogeneous solution. We don't have any initial conditions. The steady state doesn't care about the initial conditions here. So we need to start with the model, which much of it's done for us. I'll just rewrite the equivalent constants that we are given for M and K and C. Everything in base units here. So we already know it's a 1 degree of freedom system. Can make our model here, our simplified picture of what's happening. So 1 degree of freedom, I'll define this as the x of t, and our c, and our k, and our m, and we have some forcing function, f of t, acting on our system. So m, k, c are done. F of t needs to be defined now, which we'll get from this graphic here. This is happening at 3 seconds. So we have the smallest repeating pattern happens every 3 seconds. It repeats itself, ends at 6, at 9, etc. It's going to go up to 5 and then come straight back down. So it's this linear function, and we can describe this as 5t over 3 or 5/3 t, depending on how we want to write it. But that is only good for the first period, so from 0 to 3 seconds. So our f of t is going to repeat itself every 3 seconds, but if we see how it's constructed, it is not harmonic. It doesn't have sines and cosines in it. We can put mods in like we did if we wanted to plot it, but that's not how we're going to be able to solve this in a closed form way. What we want to do is expand this f of t. We need to do the Fourier series expansion of f of t. So what would we do? Well, we need to integrate it in order to find a naught. We need to integrate it times cosine function to find ans, times the sine function to find the bn's, and all of that to expand f of t so that we can have this look like what we want to get the general solution. But we've actually already done this. We did the Fourier series expansion of this exact forcing function all the way back in section 1. So you can watch that video again to refresh yourself. But the results of that were that we already found that the a naught term was 5 for this, an was 0, and all the bn was negative 5 over n pi. So this is again coming out from the Fourier series expansion. Now, had we not already done this function, we would have to do that work to get these coefficients from the Fourier series expansion. We also found that omega for this was 2 pi over t, where t was 3 seconds. So 2 pi over 3 radians per second was that fundamental frequency. It's our fundamental driving frequency that we're also going to use going forward. Now with our f of t defined, or done the Fourier series expansion of, we can put together our equation of motion. We already know it's this simple 1 degree of freedom spring mass damper system, and we know the m, the c, and the k, so we can link that all together. We're going to have mx double dot plus cx dot plus kx equals some general f of t, and now we'll expand on that, and we'll put in the values we already know. So again, our m is 2x double dot plus 30x dot plus 775x equals, and here I will put the Fourier series expanded version of f of t. So 5 over 2 plus the sum from n equals 1 to infinity. I will use this infinite sum on this one. The an terms are all 0, and the bn terms are going to be this negative 5n over n pi times the sine of omega 2 pi 3 times t. And I also need an n in here, times n times t. With the equation of motion written down, now we can go to our identify step and we can look at our equation of motion and see what we have. Looking at the left-hand side, 1 degree of freedom. It is linear. It is damped. We're going to see in a moment what kind of damping we have. And it has to be underdamped if we want to be able to use the homogeneous solution like we have been. But we're going to figure out what the damping is. And if we look at the right-hand side, now that it's expanded, it is this general forcing. At least in terms of this course, where we would go to find out how to solve this. The right-hand side, now that we've done the Fourier series expansion, we can do a general forcing like we talked about in the previous subsection. Now that we've identified it, we can see what the particular solution is going to be, which is, for this problem, all we care about, and that is the same as the steady state. It is going to be equal to our A0 over 2k plus the sum from n equals 1 to infinity of, now all of our an terms are 0, so I will drop them out from writing this one, but bn sine n omega t minus phi n over k times the square root of 1 minus n squared r squared quantity squared plus quantity 2 zeta n r squared. That's all over square root like that. Some of these things we already know, the A0, we already know the BNs, so we need a couple more of these pieces put together in our parameters. Natural frequency, root k over m, we're still in 1 degree of freedom. Our k was 775 in base units, our m was 2, so our natural frequency comes out to 19.5 radians per second. And our omega, we were already told, I'll write it down again here, 2/3 pi radians per second. That's the fundamental frequency of our forcing. This is a damped system, so we can figure out the damping is c over 2m omega n. We know all those values at this point. We get 0.381. So this is indeed an underdamped system. So we can put that detail up in the identify. We have omega n, we have omega, we have zeta. So we also want to compute this r, this ratio. And that is going to be that fundamental frequency over the natural frequency. So we get 0.106 for that. Now we will have to compute these phases, the phi n's, which we can at least look at that general equation for. The phi n's are going to be calculated using that 4-quadrant arctangent of 2 zeta nr over 1 minus n squared r squared. But we're going to need to do that for every n value, and we are going to need to compute the rest of the stuff inside of the summation for every n value. So I'm not going to write it all down, but I wrote down some of the important parameters, and now we can start to assemble and look at our solution, and then we can plot it as well. Going into the MATLAB, I can define all the things I just had in what I was able to work out by hand so far. I can identify and I can put in my Fourier coefficients. My A0, again, I already knew was 5, and then the definitions for my A's, which I'm going to make functions of n, and my B's, also functions of n. The given spring mass damper parameters, we didn't have to go through a Lagrange, in this one we were just given that. And then the parameters I was just able to calculate. So I'll at least run that so far and get some values. That's what the plot looks like of the forcing. And just to recap, so this is the R that we get, 0.106 for about, and then some of these other calculations are zeta value, our fundamental frequency, which was 2/3 pi, about 2.09, and the natural frequency. So these other things, I'm not going to try to calculate them out by hand, but I can define phi as a function of n. This is coming right from what I wrote by hand and also what's coming off the slides. So for any value of n, I can now calculate what the phi value is for that n. And then the particular solution I can put all together with this function here. So I am doing this as inline functions for this. So if I want the nth component of my particular solution, you can see how I'm doing that here. This is only the stuff inside of the summation, take note. So I do have, because I want to do this in general, I have my full numerator here that does include the an terms, but for this particular problem, they're all 0. And then the numerator with the b terms and the sine and the phi. Right? So that will be non-zero for this one. And then that lengthy denominator. So you can look back at the slides, you can look back at the handwritten work. That's where this is coming from. Again, this is just for the stuff inside of the summation. Now, I'm going to plot this for 3 forcing cycles, 3 of those fundamental forcing cycles. I could do more or less, but that's what I'm doing in 33, is just defining it for 3 of them. And I'm going to go up to 1,000 terms for comparison. And we're going to be testing for convergence, or seeing when we converge using a little bit of a different method than we used previously for the Fourier series. One thing we could do is just see how many terms until the Fourier series of the force converge to the original, the actual solution, using that mod there. So we could see how many terms it takes and use that as a basis for how many terms to take for our solution to the ODE. And keep in mind here, we are doing something different now than we did in section 1. In section 1, we were only expanding the Fourier series of, in this case, the forcing, and seeing how it compared to the original function. And that gave us a sense of how many terms does it take to converge. Here, we are solving for x of t, also using an infinite series, and it's directly related to the Fourier series, but we don't have anything to compare it to. We don't know the true answer to x of t for this problem. So we don't necessarily know how many terms to take. Maybe when the Fourier series converges to the original function for the forcing, that will be enough, but that's not necessarily going to be true. So that's why we're going to see a little bit different method here. But anyway, what I'm going to do is I am going to, in this big X term, this is going to be partial sums of my solution, of my steady state solution, the particular solution. So every row is going to be making up some partial sums. And if you see how I'm doing it in the for loop, is I am taking the entire previous row and then adding that extra little nth piece to it. Here I'm using k, but that's really the little n that I'm using. So I'm not using the cum sum here because this is already effectively doing a cum sum. Just the way I programmed this one up. I could also just do it with a cum sum, and then I wouldn't have to be adding the previous row to find my current row. But same idea I was using in section 1, just implemented a little bit differently. So every row of big X is going to be the nth partial sum. So the lower down I go in that matrix of X, the more terms I'm going to be using. Right, let me just run up till that point here. Right, so I've computed big X here, and this is somewhat for demonstration purposes, but we also want to see the convergence. So if I just print big X, okay, well, it's a lot of terms there because each row is the nth partial sum and each column is a timestamp. So what I'm going to do is kind of like what I did for just the Fourier series expansion. I'm going to plot my specific partial sums of this X. For here, I'm going to do 5 terms, 10 terms, 100 terms, just for demonstration. And we can see what the solutions look like. So keep in mind, I am looking at the steady state behavior. This is not the forcing. This is steady state, and I'm plotting this in millimeters as my y-axis. And I just somewhat randomly chose a 5 out of 10 and 100, and we see what the responses look like. When I use few terms, I'm only using 5 terms. I have a lot of these oscillations here, and then with the pink one, the 10 term, or magenta, I have also some oscillations, but they're slower. They're smaller, I should say. And then when I use 100 of these terms, we see it's a little bit tough to see in the green, but if I zoom in a little bit, the green line, I'm not seeing really any of that waviness as I'm going through, like I'm seeing with the only using 5 terms or 10 terms. So it seems to be a lot better. I do have a little bit of overshoot, it appears up here. But let me go back to the original picture. And I have a little bit of undershoot at the bottom as well. But at least graphically, it looks like those extra oscillations go away as I start adding more and more terms to my steady state or my particular series. So 100 terms looks visually to be pretty good for what the steady state behavior of this system is. It looks to go up a little bit past 6 millimeters as its maximum value, and then it goes back to around, let's say, negative 1.25 or so. I guess I can just click here and get a rough idea of what the maximum and the minimum is, assuming that the green, the 100 term, is the most accurate one. So it goes up to a maximum of about 6.3 and a minimum value, if it lets me, of negative 1.4. So overall, we're seeing that this mass is basically following the same profile as the forces at steady state, which matches more or less what we've been seeing when we have forcing, is that once those transients die out, that the output is going to match the input, maybe with a phase delay and with a different amplitude. And certainly we have a different amplitude because our output is in millimeters and our input was in newtons. But how can we know we can trust the green solution, the 100-term solution? This is where we're going to be looking at convergence. And again, I'm going to use root mean squared error as a metric to see when we have converged to get an idea of that. Now, the downside of looking at the steady state behavior, the output of the system, is I don't know the true value here. I don't have the closed form solution because, well, that's what I developed, is a closed form solution, but that uses an infinite number of terms. So if you use an infinite number of terms, then yes, I do have the exact closed form solution. But how do I know when I've used enough terms that my error is going to be sufficiently small? That's where we'll use an RMSE convergence. So what I'm going to do here is, for every term, let's say the 100th term, using 100 partial sums, what I'm going to do is compare it to the previous. So I'm going to subtract the partial when I was using 99 terms and see what the difference is. And that's the RMSE I'm going to use, is the difference between neighboring partial sums. So I'll compare what's the RMSE with the 100 term versus the 99, the 101 versus the 100, the 1000th versus the 999th, and find the root mean squared error between those. So what I should expect is that RMSE, the difference between the series, should get smaller and smaller. So basically, as I add more terms, the little differences between like the 101st partial sum versus the 100th should be really small. So I should see barely any RMSE between neighboring terms as I use a sufficient number of terms. So that's what we're comparing here. It's a little bit different than what we did in the past, where we were looking at the RMSE between the true value and the nth partial sum. Here, we're looking at the RMSE between the nth and the nth minus 1 partial sum. And we'll see what graphically it's going to look like. This is what we get. I'll still do it in this semi-log. So the x is in semi-log. This is the number of terms and then the y is the RMSE value that it has with the time series using one fewer term, the one before it. So we can see what's happening when we use barely any terms. What we're going to have is a lot of difference as we keep adding that one more term. The RMSE is at least relatively high, and it drops pretty rapidly. And then once we get to about n is 30, maybe let's say 40. So using about 40 terms, it appears relatively flat, that the RMSE is pretty constant. It's not changing as drastically once we start using about 40 terms. Now, there is still an RMSE. There's still a difference between the neighboring partial sums, but it's really small compared to earlier on when the RMSE between those terms was high. So this is generally we can say that once we get to maybe about 50 terms, adding that one more term is barely changing the RMSE. Again, this is relative to when we were at below 50 terms. Adding that extra term there did make the RMSE smaller, so there was some appreciable difference between the partial sums. So I would say in general terms here, visually at least, that if we use at least 50, if big N is at least 50, that we're getting pretty low error between our approximation of the 50th or higher partial sum and the true value. So when we used 100, just kind of picking it out in the other plot, that 100, that green line, this is showing by the convergence plot that yes, this is pretty reliable. The error is probably pretty small by only using 100 terms versus using an infinite number of terms. Again, that's coming from this convergence plot and seeing it's basically that RMSE becomes flat by the time we use about 50 in our partial sum. So what we've done here is we do have the steady state solution. I didn't write it out because we are using these infinite series, or really we're using partial sums of them, and they are being calculated in MATLAB what all of those terms are, and just kind of automating the process. But by hand, we did need to figure out some of those parameters. Now, for this problem, we were given the Fourier series coefficients. In general, we would have to solve for them first before we can go on and actually find the closed form solution for the particular solution.